Welcome to Science for Sleep. Tonight, we will listen to the universe without sound. We will follow events so powerful that they reshape space itself, yet arrive to us as the faintest of whispers. Far beyond stars and galaxies, beyond light and color, there are moments when the universe changes forever. These moments do not flash or roar. They do not announce themselves with explosions or fire. Instead, they pass quietly through everything, leaving behind gentle ripples in the structure of reality. Tonight, we are listening to those ripples. We are listening to black holes colliding in silence. Long before any telescope was built, long before any equation was written, the universe was already moving. Massive objects drifted through space, drawn together by gravity, orbiting one another in slow, inevitable dances that lasted millions or even billions of years. These movements bent space and stretched time in ways that no human could have noticed. There was no sound to hear, no light to see, no signal that could reach a waiting observer. And yet, something profound was happening. The universe was vibrating, softly and continuously, like a vast instrument being played far beyond the range of human senses. For most of human history, space was believed to be perfectly silent and perfectly still. Stars appeared fixed. Galaxies were unknown. Even the idea that space and time could move, stretch, or ripple was unimaginable. The night sky looked calm and unchanging, a quiet backdrop to life on Earth. But that calm was an illusion created by distance and scale. Beneath that stillness, gravity was constantly at work, guiding matter into stars, stars into galaxies, and galaxies into massive structures that spanned unimaginable distances. Every movement, no matter how slow, left an imprint on the universe itself. Gravity is often described as a force, but that description barely captures its true nature. Gravity is not something that simply pulls objects together like an invisible rope. It is a shaping influence, a way that mass and energy tell space how to curve and tell time how to flow. When massive objects move through space, they do not travel across a rigid stage. They move across a fabric that responds to their presence. That fabric bends, stretches, and relaxes, always adjusting to the distribution of mass within it. Most of the time, these adjustments are gentle and steady, creating orbits that persist for eons. But when extremely massive objects move rapidly, something else occurs. The fabric itself begins to ripple. These ripples are known as gravitational waves. They are not waves of sound or light. They are waves of space and time. They carry no color, no temperature, no electric charge. They do not glow or reflect. They simply pass through, compressing space in one direction while stretching it in another, then reversing the pattern as they move onward. A gravitational wave can pass through planets, stars, and even human bodies without leaving any visible trace. It does not disturb atoms or disrupt molecules. It simply changes distances by amounts so small that they remain far below everyday experience. For decades, gravitational waves existed only as a prediction. They emerged from equations that described gravity not as a force acting at a distance, but as a geometric property of the universe. According to these equations, accelerating masses should generate ripples in space-time, much like a moving object creates waves on the surface of water. But unlike water waves, gravitational waves do not require a medium. They do not fade easily. They travel at the speed of light and carry information about the events that created them across the universe, unchanged by dust, gas, or darkness. At first, Many scientists doubted that these waves could ever be detected. The effects were expected to be extraordinarily small. Even the most violent events in the universe would produce distortions far smaller than the width of an atomic nucleus by the time they reached Earth. Measuring such changes seemed impossible. Instruments would need to detect differences in distance smaller than anything ever measured before, while filtering out vibrations from the Earth itself, from thermal noise, and from countless other sources of interference. For a long time, gravitational waves remained a beautiful idea, admired for its elegance, but disconnected from observation. Meanwhile, the universe continued its quiet activity. Black holes formed when massive stars exhausted their fuel and collapsed under their own gravity. Some black holes drifted alone through space, remnants of ancient stellar deaths. Others formed in pairs, bound together by gravity from their earliest moments. These binary black holes orbited each other slowly at first, separated by vast distances. Over time, their orbits tightened. With each revolution, they lost a tiny amount of energy, carried away not by light, but by gravitational waves. The system became more compact, the motion faster, the ripples stronger. Yet this entire process unfolded in darkness, invisible and silent. Black holes themselves are often misunderstood. They are not cosmic vacuums pulling everything toward them indiscriminately. From a distance, a black hole behaves like any other object of the same mass. Its gravity governs the motion of nearby stars and gas in predictable ways. What makes a black hole unique is not its pull, but its density. A black hole contains an enormous amount of mass compressed into an incredibly small region of space. This extreme concentration bends space-time so strongly that beyond a certain boundary, not even light can escape. And that boundary is known as the event horizon. Despite their reputation, black holes are among the simplest objects in the universe. They have no surface, no texture, no internal structure that can be observed from the outside. They are defined entirely by a small set of properties: mass, spin, and charge. Everything else about the matter that formed them is erased from view. This simplicity makes black holes ideal sources of gravitational waves. When two black holes orbit one another, their motion is governed by gravity alone, free from the complications of matter, radiation, or magnetic fields. The waves they produce are clean, precise signatures of space-time itself in motion. As two black holes spiral closer together, their orbits accelerate. Each pass releases more energy in the form of gravitational waves. The frequency of these waves increases steadily, tracing a rising pattern that reflects the tightening dance of the pair. This phase is known as the inspiral, and it can last for millions of years. For most of that time, the waves are too weak to be detected, spreading gently across the universe. But as the black holes draw nearer, the ripples grow stronger, their rhythm quickening as the system approaches its final moments. Eventually, the black holes reach a point where no stable orbit remains. In a fraction of a second, they merge into a single, larger black hole. This merger releases an immense amount of energy, more than is emitted by all the stars in the observable universe combined during that brief instant. Yet none of this energy appears as light. There is no flash, no visible explosion, when almost all of it is carried away by gravitational waves, surging outward in all directions. This is the moment when the universe's quiet symphony reaches its crescendo. After the merger, the newly formed black hole is not immediately still. It vibrates, ringing like a struck bell, as it settles into a stable shape. This phase is known as the ring down. The vibrations gradually fade as energy continues to radiate away in gravitational waves. What remains is a black hole defined once again by mass and spin, calm and silent, indistinguishable from any other of its kind. The entire event, from in-spiral to merger to ring down, lasts only seconds for distant observers, but it leaves behind a lasting imprint on space-time that can travel across billions of light years. For most of cosmic history, these events went unnoticed. Gravitational waves passed through galaxies, stars, and planets without detection. They crossed Earth long before life emerged, long before continents formed, long before humans walked upright. Space itself carried the memory of ancient collisions, but there was no instrument capable of listening. The universe was full of stories, but no ears to hear them. That changed only recently. After decades of theoretical work and experimental effort, humanity finally built instruments sensitive enough to detect gravitational waves directly. These detectors do not listen in the conventional sense. They do not record sound. Instead, they measure changes in distance caused by passing waves, tracking how space itself stretches and contracts by unimaginably small amounts. When a gravitational wave passes through such a detector, like it alters the length of its arms by less than 1,000th the size of a proton. And yet, with enough precision and care, these changes can be measured. The first confirmed detection of gravitational waves marked a turning point in science. It was not just a confirmation of a long-standing prediction. It was the opening of an entirely new way of observing the universe. For the first time, humanity could study cosmic events that emit no light, no particles, no electromagnetic signals of any kind. Black hole mergers, once completely hidden, became observable through their effect on space-time itself. The universe had gained a new voice, one that spoke not in photons, but in geometry. Listening to gravitational waves is often compared to hearing music, but the analogy goes deeper than metaphor. Just as sound carries information through vibrations in air, gravitational waves carry information through vibrations in space-time. Their frequencies, amplitudes, and patterns encode details about the masses of black holes, their spins, their distances, and the nature of gravity itself. Each detection is a cosmic composition, shaped by the dynamics of the system that created it. Together, these signals form a growing archive of the universe's most extreme events. And yet, despite the power behind them, gravitational waves remain gentle by the time they reach us. The universe does not shout, it whispers. These whispers pass through Earth constantly, unnoticed by our senses. They pass through oceans without stirring water, through mountains without cracking stone, through bodies without sensation. So they are reminders that the most dramatic events in existence do not announce themselves loudly. They simply happen, and the universe carries on. Tonight, we are following these whispers back to their source. We are tracing ripples across space and time, listening not with ears, but with understanding. We are exploring how silence can carry meaning, how absence of sound can still tell a story. Black holes collide without noise, without light, without warning. And yet, in that silence, the universe reveals some of its deepest truths. As we continue, we will move slowly. We will follow gravity's patient work across cosmic time. We will examine how space-time responds to motion and mass, how waves travel without resistance, and how human instruments learn to detect signals smaller than anything previously measurable. We will see how these waves connect distant events to our own quiet corner of the cosmos, passing through Earth as effortlessly as they pass through the void. This is not a story of destruction, but of transformation. Not a story of chaos, but of order emerging from motion. The gravitational wave symphony is always playing, whether we listen or not. Tonight, we are simply tuning in. Gravitational waves did not emerge from imagination or metaphor. They arose from a fundamental rethinking of what gravity is. For centuries, gravity was understood as a force acting instantaneously across distance, a silent pull connecting masses through empty space. This view explained planetary motion with remarkable accuracy, but it treated space and time as fixed, passive backgrounds. In the early 20th century, that picture changed. Gravity was redefined not as a force, but as a consequence of geometry. Space and time became active participants in the universe's behavior, capable of bending, stretching, and responding to mass and energy. In this geometric view, massive objects do not merely move through space. They reshape it. A star curves the space around it. A planet follows that curvature, not because it is being pulled, but because it is moving along the straightest possible path through a warped landscape. Time itself slows in regions of strong gravity, ticking at different rates depending on position and motion. These effects are subtle near Earth, but they become extreme near dense objects like neutron stars and black holes. When such objects move, especially when they accelerate, the curvature they create cannot adjust instantly. Instead, changes propagate outward as waves. These gravitational waves are not disturbances within space. They are disturbances of space. They represent oscillations in the distances between points, even when no matter occupies those points. As a wave passes, space is stretched in one direction and compressed in the perpendicular direction. Then the pattern reverses. This stretching and compressing occurs rhythmically as the wave moves forward. The effect is incredibly small, but it is real. Distances change. Clocks tick differently. The geometry of the universe briefly oscillates before returning to equilibrium. One of the most important properties of gravitational waves is that they interact extremely weakly with matter. Unlike light, which can be absorbed, scattered, or blocked by dust and gas, gravitational waves pass through almost everything unimpeded. Entire galaxies offer no resistance. Dense clouds of gas barely affect them. Even the matter inside stars does not significantly alter their path. This makes gravitational waves ideal messengers from distant regions of the universe. They carry information directly from their source, largely unchanged by the space they traverse. This transparency also makes them extraordinarily difficult to detect. By the time a gravitational wave reaches Earth, even one generated by a catastrophic black hole merger, its effect is minuscule. The stretching of space amounts to a fractional change in length of about 1 part in 10,000 trillion. To measure this, detectors must compare distances with a precision that defies intuition. They must remain stable against seismic vibrations, must thermal fluctuations, and even the quantum behavior of light itself. Detecting gravitational waves is not about amplifying a signal. It is about eliminating noise. Before discussing how detection became possible, it is important to understand why black holes are such efficient sources of gravitational waves. Any accelerating mass produces gravitational radiation, but most everyday motions involve masses that are far too small, or accelerations that are far too gentle to generate detectable waves. Even planets orbiting stars produce gravitational waves, but the energy involved is negligible. To produce strong waves, two conditions must be met. The masses must be enormous, and the motion must involve rapid acceleration or extreme curvature of space-time. Binary systems composed of compact objects meet these requirements perfectly. Neutron stars and black holes pack the mass of stars into regions only kilometers across. When two such objects orbit each other, they move at significant fractions of the speed of light. Their gravitational fields are intense and rapidly changing. This combination makes them powerful emitters of gravitational radiation. As the system evolves, energy is carried away by the waves, causing the orbit to shrink. This process is slow at first, but it accelerates dramatically as the objects draw closer together. For binary black holes, this in-spiral phase dominates the system's lifetime. For millions or billions of years, the pair may orbit at great distances, emitting weak gravitational waves. As energy is lost, the orbit tightens and speeds up. The gravitational waves grow stronger and their frequency increases, and this gradual rise encodes detailed information about the masses and spins of the black holes. The final seconds of in-spiral are the most energetic and produce the strongest signals. But they represent only the closing moments of a very long cosmic history. During the merger itself, the two black holes coalesce into a single entity. This is one of the most extreme events allowed by the laws of physics. Space and time are violently distorted in a region smaller than a city, yet involving masses tens of times greater than the sun. The geometry of space-time changes rapidly as the system transitions from two separate horizons to one. The gravitational waves emitted during this phase reach their peak amplitude, carrying away enormous amounts of energy in a brief burst. After the merger, the newly formed black hole is not perfectly stable. It oscillates, emitting gravitational waves as it settles into its final configuration. These oscillations depend only on the black hole's mass and spin, not on the details of how it formed. This simplicity is a consequence of the fundamental nature of black holes. They have no internal structure that can be observed from the outside. The ring-down phase acts like a signature, confirming that the object formed is indeed a black hole described by the equations of gravity. Understanding these phases required decades of theoretical work. Early calculations treated gravitational waves as weak perturbations, valid only when space-time curvature was small. But black hole mergers involve extreme curvature, where simple approximations fail. Solving the full equations governing space-time dynamics in these regimes required new mathematical techniques and powerful computers. Numerical simulations became essential. By modeling the in-spiral, merger, and ring-down of black holes in detail, scientists could predict the exact waveforms expected from different systems. These predicted waveforms became templates, patterns against which real data could be compared. Without them, detection would have been impossible. Gravitational wave signals are buried in noise, indistinguishable to the eye. Only by knowing precisely what to look for could scientists extract meaningful signals from the background. This approach transformed gravitational wave astronomy into a precise science, capable of measuring properties of distant systems with remarkable accuracy. The detectors themselves rely on a simple principle. They measure changes in distance using laser interferometry. A laser beam is split into two perpendicular paths, each traveling down a long tunnel before reflecting off a mirror and returning. When the beams recombine, they produce an interference pattern that depends on the relative lengths of the paths. If a gravitational wave passes through the detector, it alters these lengths differently, changing the pattern. By monitoring this change, scientists can infer the presence of a wave. The challenge lies in making these measurements precise enough. The mirrors must be isolated from vibrations caused by earthquakes, passing vehicles, and even ocean waves on the other side of the planet. The laser must remain stable. The entire system must operate in a near-perfect vacuum. Even the pressure of photons striking the mirrors can introduce noise. Every conceivable disturbance must be accounted for and minimized. Despite these challenges, detection became possible through persistence and refinement. When the first gravitational wave signal was confirmed, it marked the beginning of a new era. For the first time, humanity could observe black holes directly, not by their influence on nearby matter, but through the waves they generate as they move. This confirmed that black holes exist as predicted, and that space-time behaves as described by theory, even under extreme conditions. Gravitational wave astronomy differs fundamentally from traditional astronomy. Telescopes collect light emitted or reflected by objects. This light can be altered by intervening material, and many objects emit little or no light at all. Gravitational waves, by contrast, are generated by motion itself. They provide a direct record of dynamics. They reveal how massive objects move, collide, and merge, independent of whether they shine. This difference opens a new window on the universe. Entire populations of black holes that are invisible to telescopes become accessible. Systems embedded in dense regions or obscured by dust can be studied. Events that occurred billions of years ago can be detected today, their waves still traveling through space. Each detection adds to a growing map of the universe's most extreme phenomena. Importantly, gravitational waves also allow tests of fundamental physics. The way waves propagate, their speed, their polarization, and their decay, all reflect the underlying laws governing space-time. By comparing observations to predictions, scientists can test whether gravity behaves as expected or whether new physics emerges under extreme conditions. So far, observations have confirmed existing theories with remarkable precision, even in regimes far beyond previous tests. As more detectors come online and sensitivity improves, the gravitational wave background becomes richer. Not every signal stands alone. Many events overlap, forming a continuous background hum produced by countless distant mergers. This background is not noise. It is a collective record of cosmic history, a persistent vibration that fills the universe. Extracting information from this background requires patience and careful analysis, but it promises insights into populations of objects too distant or too numerous to resolve individually. The universe, viewed through gravitational waves, is dynamic in a new way. It is not just a collection of objects in space, but a constantly evolving geometry. Space stretches and relaxes. Time speeds up and slows down. Massive objects trace paths that send ripples outward, connecting distant regions through the fabric of space-time. This view challenges intuition, but deepens understanding. As we move forward, we will explore how these waves travel across cosmic distances, how they interact with the expanding universe, and how their detection allows us to reconstruct events that occurred long before Earth existed. We will examine how silence carries structure, how absence of light does not mean absence of information, and how listening to space-time itself reveals a universe far more active than it appears. The gravitational wave symphony does not rely on sound, but on motion. It does not depend on observers, but on geometry. It has been playing since the earliest moments of cosmic history, uninterrupted and pervasive. With the tools now available, humanity has begun to hear it, not as noise, but as a coherent, meaningful pattern written into the universe itself. Gravitational waves do not travel through a static universe. As they move outward from their source, they pass through a cosmos that is expanding, evolving, and changing shape over time. This journey across space and time subtly alters the waves themselves. Their frequencies stretch as the universe expands, their wavelengths growing longer as the distance between galaxies increases. By the time a wave reaches Earth, it carries not only information about the event that created it, but also a record of the space it has crossed. In this way, as gravitational waves become messengers of both local violence and cosmic history. The expansion of the universe affects gravitational waves in a manner similar to its effect on light. Just as light from distant galaxies is red-shifted, stretched to longer wavelengths as space expands, gravitational waves experience an analogous stretching. The signal emitted during a black hole merger billions of years ago arrives at Earth with a lower frequency than it had at its source. This red shifting allows scientists to estimate the distance to the event and place it within the broader timeline of cosmic evolution. Each detection thus becomes a point of reference, linking the present to the deep past. Unlike light, however, gravitational waves are not easily absorbed or scattered. Dust clouds that obscure entire galaxies have no effect on them. There were intervening stars and gas pass unnoticed. Even the intense gravitational fields of other massive objects do not significantly alter their path. This makes gravitational waves uniquely reliable carriers of information. They provide a clear line of sight to regions of the universe that are otherwise hidden, revealing events that would remain invisible through electromagnetic observation alone. As waves travel, they gradually weaken, spreading their energy across an ever-growing spherical front. This dilution follows precise mathematical rules, allowing scientists to calculate how strong a signal should be at a given distance. By comparing observed amplitudes to predicted ones, researchers can infer how far away a merger occurred. This method does not rely on intermediate calibration or assumptions about the brightness of sources. It is a direct geometric measurement, rooted in the structure of space-time itself. One of the most remarkable aspects of gravitational wave detection is that it allows measurements of distance without the need for traditional distance ladders. In astronomy, distances are often estimated through chains of indirect methods, each relying on assumptions that introduce uncertainty. Gravitational waves bypass many of these steps. The waveform itself encodes the absolute scale of the system. This makes gravitational wave sources powerful tools for studying the expansion rate of the universe, offering independent checks on measurements obtained through other means. The waves that reach Earth do not arrive in isolation. They arrive amid constant motion. Our planet rotates. It orbits the sun. The sun moves through the Milky Way. The galaxy itself drifts through intergalactic space. All of this motion must be accounted for when interpreting signals. Detectors must distinguish between changes caused by passing waves and those arising from local motion or environmental disturbances. This requires careful modeling and precise timing. To achieve this, gravitational wave observatories operate in coordinated networks. Multiple detectors positioned far apart can compare signals, confirming that a wave passed through Earth and determining its direction of origin. A true gravitational wave will arrive at each detector at slightly different times, depending on its path across the planet. By analyzing these delays, scientists can triangulate the source's location in the sky. This process transforms fleeting distortions into maps of cosmic events. These networks also improve confidence in detections. Local disturbances affect only individual detectors. A passing truck, a small earthquake, or a gust of wind can produce signals that mimic certain features of gravitational waves. But a true astrophysical signal will appear consistently across multiple instruments, separated by thousands of kilometers. Agreement between detectors provides strong evidence that the signal originates beyond Earth. As detection rates increase, patterns begin to emerge. Black hole mergers are not evenly distributed in mass or frequency. Some involve black holes only a few times more massive than the Sun. Others involve objects tens of times heavier. These distributions offer clues about how black holes form and evolve. They reflect the life cycles of stars, the environments in which they are born, and the history of star formation across the universe. One surprising discovery from early detections was the prevalence of relatively heavy black holes. Prior observations had suggested that stellar mass black holes might cluster around certain masses. Gravitational wave detections revealed a broader range, including objects heavier than expected. This prompted new investigations into how massive stars collapse, how much mass they lose before death, and how different environments influence their evolution. The spins of black holes also carry important information. Spin affects the waveform, subtly altering its shape. By measuring these effects, scientists can infer how fast black holes were rotating before merging and how their spins were oriented relative to their orbit. These details hint at the history of the system. Black holes formed together from a binary star may have aligned spins, while those that formed separately and later paired through chance encounters may show random orientations. Beyond black holes, gravitational waves also reveal neutron star mergers. Neutron stars are dense remnants of massive stars that did not collapse into black holes. When two neutron stars merge, they produce gravitational waves along with bursts of light across the electromagnetic spectrum. These events offer opportunities to combine gravitational and electromagnetic observations, enriching understanding of nuclear physics, matter under extreme pressure, and the origins of heavy elements. In contrast, black hole mergers are often silent in light. They produce gravitational waves alone, without accompanying flashes or bursts. This silence makes them pure probes of gravity. They allow tests of how space-time behaves when stripped of complicating factors like matter and radiation. Each black hole merger becomes a controlled experiment conducted by the universe itself. As observations accumulate, scientists begin to detect not just individual events, but the collective effect of many distant sources. This manifests as a stochastic gravitational wave background, a persistent signal created by the superposition of countless unresolved mergers throughout cosmic history. This background is faint, but it carries information about populations of objects across time and space. Detecting and characterizing it requires long-term observation and careful statistical analysis. The gravitational wave background is analogous to the cosmic microwave background in light, but it arises from motion rather than temperature. It reflects the integrated history of compact object mergers, including those too distant or too weak to detect individually. Studying this background can reveal how frequently black holes and neutron stars formed and merged in different eras of the universe's evolution. Gravitational waves also offer insights into the earliest moments after the Big Bang. Some theories predict that processes in the early universe generated primordial gravitational waves, leaving imprints that persist today. Detecting these signals would provide direct evidence of conditions that existed fractions of a second after cosmic expansion began. Unlike light, which cannot travel freely until the universe becomes transparent, gravitational waves can carry information from epochs otherwise inaccessible. While such primordial signals remain elusive, the search continues. Improved detectors, longer observation times, and refined analysis techniques gradually increase sensitivity. Each incremental improvement brings the possibility of detecting fainter and older signals, extending our reach deeper into cosmic history. Listening to the universe through gravitational waves reshapes perspective. It emphasizes motion over appearance, dynamics over form. It reveals a universe that is constantly active, even when it appears still. Massive objects move, collide, and merge, reshaping space-time in subtle but profound ways. These changes propagate outward, linking distant regions through a shared geometric framework. This view also underscores the interconnectedness of the cosmos. Events that occur in remote galaxies affect the geometry of space everywhere. Their waves pass through Earth, altering distances by minuscule amounts, reminders that we are embedded within a larger, dynamic system. Even in silence, the universe communicates. As detection capabilities advance, gravitational wave astronomy transitions from discovery to exploration. Patterns become clearer. Statistics improve. New classes of sources may emerge. Each detection refines understanding of gravity, matter, and cosmic evolution. The symphony grows richer, its themes more complex. Black holes begin their existence not as cosmic anomalies, but as the final stage in the life of massive stars. When a star many times more massive than the Sun exhausts the nuclear fuel that supports it against gravity, its core collapses. In the most extreme cases, this collapse proceeds unchecked, compressing matter into a region so dense that space-time curves inward on itself. The result is a black hole, an object whose defining feature is not what it contains, but how it reshapes the space and time around it. From the outside, the details of its formation vanish, leaving behind a simple gravitational presence that persists for billions of years. Once formed, black holes do not exist in isolation by necessity, but many find themselves bound to companions. Some are born in binary systems, where two massive stars orbit each other from birth. When both stars collapse, they leave behind a pair of black holes locked in a shared gravitational relationship. Others form alone and later acquire companions through encounters in dense stellar environments, such as globular clusters or galactic centers. And in these crowded regions, close gravitational interactions can pair black holes that were once strangers, creating binaries whose histories are written into the waves they will eventually emit. The environment in which a black hole binary forms influences its future evolution. Binaries born from stellar pairs tend to have aligned spins and relatively circular orbits. Those formed through capture in dense environments may exhibit misaligned spins and more complex orbital dynamics. These differences affect the gravitational waves produced during inspiral and merger. Subtle variations in waveform shape and code information about the system's origin, allowing scientists to reconstruct aspects of its past long after the event has concluded. As a black hole binary evolves, it interacts with its surroundings. In the early stages, interactions with nearby stars or gas clouds can alter the orbit, gradually hardening the binary by extracting energy. Over time, these interactions become less important as the black holes draw closer together. Eventually, gravitational wave emission becomes the dominant mechanism driving the system's evolution. At this point, the binary enters a phase governed almost entirely by space-time dynamics. During this gravitationally dominated inspiral, the black holes orbit each other at increasing speeds. Their paths are not simple circles, but complex trajectories shaped by relativistic effects. Time dilation, frame dragging, and nonlinear space-time curvature all influence motion. These effects are not abstractions. They leave measurable imprints on the gravitational waves emitted, altering their phase and amplitude in ways that can be detected with sufficient precision. Frame dragging, caused by the rotation of massive objects, twists space-time around spinning black holes. This effect causes the orbital plane of the binary to precess, slowly changing its orientation over time. This precession modulates the gravitational wave signal, adding complexity to its structure. By analyzing these modulations, scientists can infer the spins of black holes and how they interact with orbital motion. As the inspiral progresses, the black holes approach velocities that are significant fractions of the speed of light. At these speeds, classical descriptions of motion fail. Relativistic corrections become essential. The gravitational waves produced during this phase are rich in information, not reflecting the intricate interplay between mass, motion, and geometry. Each cycle of the orbit adds another oscillation to the wave, each one slightly different from the last. The final moments of inspiral occur rapidly. The separation between the black holes shrinks to just a few times the size of their event horizons. The waves rise sharply in frequency and amplitude. This rapid evolution produces the characteristic chirp observed in gravitational wave detections, a rising tone translated from geometric oscillations into an audible representation. While the sound itself is a human construction, the pattern it represents is a faithful encoding of space-time's response to extreme motion. At the moment of merger, the two event horizons join. This is not a collision in the conventional sense. There is no impact, no surface contact. Instead, space-time itself reorganizes. The geometry transitions from one configuration to another, governed by the equations of gravity. During this transition, space-time emits its strongest gravitational radiation, carrying away excess energy and angular momentum. The details of this process are complex, but remarkably, the outcome is simple. A single black hole emerges, defined by its final mass and spin. The ring-down phase that follows is characterized by damped oscillations. The newly formed black hole vibrates in specific modes determined solely by its properties. These modes decay over time as energy continues to radiate away. The frequencies and decay rates of these oscillations provide a stringent test of gravitational theory. Observations so far have matched predictions closely, confirming that black holes behave as expected even under the most extreme conditions. This simplicity is not accidental. It reflects a deeper principle in gravitational physics. Black holes, regardless of how they form, lose nearly all information about their past through gravitational radiation and horizon formation. The waves emitted during merger encode the final adjustments needed to reach a stable configuration. Once this process is complete, the black hole becomes indistinguishable from any other, with the same mass and spin. The energy carried away by gravitational waves during a black hole merger is immense. In some cases, several solar masses worth of energy are radiated in seconds. This energy does not heat surrounding space or illuminate nearby matter. It travels outward as pure geometry, and stretching and compressing space-time as it goes. By the time it reaches Earth, it is faint, but its signature remains intact. Detecting these signals requires translating geometric changes into measurable quantities. Detectors do not observe black holes directly. They observe the consequences of their motion encoded in passing waves. Each detection is a reconstruction, piecing together distant events from subtle clues embedded in data. This process depends on careful calibration, precise modeling, and rigorous statistical analysis. As gravitational wave observatories improve, they detect weaker and more distant events. The population of observed black holes grows, revealing trends and anomalies. Some black holes appear heavier than expected, suggesting formation channels involving multiple mergers or unusual stellar evolution. Others exhibit spins that challenge existing models. Each new detection refines understanding and prompts revisions to theory. Gravitational wave observations also inform astrophysics beyond black holes themselves. They provide insights into star formation rates, the evolution of galaxies, and the distribution of mass across cosmic time. Black hole mergers trace regions where massive stars once lived, linking present observations to past conditions. In this way, gravitational waves become tools for studying the broader structure and evolution of the universe. The study of black hole collisions is not complete. Many questions remain unanswered. How common are different formation pathways? How do environments influence merger rates? Are there populations of black holes that remain undetected? Gravitational waves offer a path toward answers, one detection at a time. The ability to detect gravitational waves depends on measuring distance with a level of precision that challenges the limits of physical measurement. At the core of modern detectors is the principle of laser interferometry, a method that compares the lengths of two perpendicular paths using coherent light. Under ordinary conditions, these paths remain equal. When a gravitational wave passes, space-time itself is distorted, stretching one path while compressing the other. The difference is extraordinarily small, but it is measurable with sufficient care and stability. Each detector consists of long vacuum tunnels arranged in an L shape. Laser light travels down these tunnels, reflects off suspended mirrors, and returns to a central point where the beams recombine. The resulting interference pattern is exquisitely sensitive to changes in path length. A passing gravitational wave alters this pattern in a characteristic way, producing a signal that can be extracted from the data. This measurement does not capture an image or a sound. It records a time series of geometric distortion. The mirrors used in these detectors are among the most precisely engineered objects ever created. They are suspended in complex isolation systems designed to minimize vibrations from the Earth, seismic noise from distant earthquakes, ocean waves impacting coastlines, and even human activity can produce disturbances orders of magnitude larger than the signals being sought. To counter this, the mirrors are hung from multiple stages of pendulums, each reducing motion across different frequency ranges. The entire system operates in a high vacuum to eliminate interference from air molecules. Even with such isolation, noise remains. Thermal motion within materials causes atoms to vibrate. Photons exert pressure on mirror surfaces. Electronic components introduce fluctuations. Each source of noise must be characterized and reduced. Engineers and physicists work together to model these effects, developing strategies to suppress or subtract them. The success of gravitational wave detection rests as much on noise control as on signal amplification. Timing is critical. Gravitational wave signals are transient, lasting seconds or less for most detected events. To distinguish them from noise, detectors must record data continuously and with precise timestamps. Atomic clocks synchronize measurements across observatories separated by thousands of kilometers. This synchronization allows scientists to compare arrival times and confirm that a signal is astrophysical in origin. When a candidate signal appears, it is subjected to extensive scrutiny. Automated algorithms search data streams for patterns matching predicted waveforms. These algorithms operate continuously, scanning vast datasets in real time. When a potential match is found, it triggers further analysis. Human oversight follows, with teams examining the data for consistency, checking environmental monitors, and ruling out terrestrial causes. Confidence in a detection arises from multiple lines of evidence. The signal must appear in more than one detector, with consistent timing and waveform characteristics. Must align with theoretical predictions for plausible astrophysical sources. Statistical analysis must demonstrate that the probability of a false alarm is exceedingly low. Only after these criteria are met is a detection announced. This process transforms fleeting distortions into reliable scientific observations. Each confirmed detection becomes part of a growing catalog. Over time, this catalog reveals patterns. Merger rates can be estimated. Population properties can be inferred. Rare events can be identified and studied in detail. Gravitational wave astronomy evolves from novelty to routine observation. As detectors improve, sensitivity increases. Upgrades involve enhancing laser power, refining mirror coatings, improving isolation systems, and implementing advanced data analysis techniques. Each improvement extends the observable volume of the universe. Events that were once too distant or too weak become detectable. The number of observed mergers grows rapidly as sensitivity increases. Global collaboration plays a crucial role. Detectors in different regions complement one another, increasing coverage and reliability. When multiple observatories operate simultaneously, localization improves. Sources can be identified more precisely in the sky, facilitating follow-up observations with traditional telescopes when applicable. This coordinated approach turns individual instruments into a global listening network. The development of gravitational wave observatories reflects decades of effort. Early prototypes demonstrated feasibility, but lacked sensitivity. Gradual improvements built confidence. Funding, collaboration, and persistence were essential. Many researchers worked for years without direct detections, motivated by the conviction that the universe had something to reveal. When signals finally arrived, they validated not only theoretical predictions, but also the patience invested in experimental design. Gravitational wave detection represents a shift in how humanity observes the cosmos. Instead of relying solely on electromagnetic radiation, it listens to motion itself. This shift broadens the range of observable phenomena. Black hole mergers, once invisible, become accessible. The universe's most extreme events enter scientific discourse not as speculation, but as measured reality. These observations also influence understanding of gravity itself. Each detection tests predictions under conditions unattainable in laboratories. Deviations from expected waveforms could indicate new physics. So far, observations have aligned closely with established theory, reinforcing confidence in current models. Yet the possibility remains that future detections may reveal surprises. The data collected by gravitational wave observatories is archived and shared, enabling independent analysis and long-term study. As datasets grow, new methods emerge. Machine learning techniques assist in pattern recognition. Improved simulations refine waveform templates. The field evolves rapidly, driven by both technological innovation and theoretical insight. Beyond current observatories, plans for future detectors promise even greater sensitivity. Space-based interferometers will operate free from terrestrial noise, capable of detecting lower frequency waves produced by supermassive black hole mergers and other large-scale phenomena. These instruments will extend listening to different regions of the gravitational spectrum, enriching the symphony with new voices. The expansion of observational capabilities deepens connection to cosmic processes. Events occurring billions of years ago influence measurements today. Waves generated in distant galaxies reach Earth after journeys spanning most of the universe's history. Detection links present observers to ancient motions, compressing vast temporal distances into moments of insight. As gravitational wave astronomy matures, it becomes integrated with other observational methods. Combined analyses incorporate light, neutrinos, and gravitational waves, creating a multi-messenger approach. This synthesis enhances understanding of complex events, revealing aspects inaccessible through any single channel. Gravitational waves move through the universe with a remarkable indifference to the matter they encounter. Unlike light, which can be absorbed by atoms, scattered by dust, or bent sharply by gravity, gravitational waves pass through nearly everything without resistance. This property arises from their nature. They are not disturbances traveling through matter. They are oscillations of space-time itself. Matter does not block them because matter is embedded within the very geometry that is oscillating. As a gravitational wave approaches Earth, it does not slow down, weaken abruptly, or fragment. It arrives as a coherent pattern of stretching and compression, sweeping across the planet at the speed of light. The distances between points on Earth change minutely as the wave passes. Mountains move closer together and then farther apart by less than the diameter of an atomic nucleus. Oceans expand and contract imperceptibly. The planet responds elastically, returning to its original configuration as the wave moves on. Human bodies are affected in exactly the same way. The distances between cells change by vanishingly small amounts. Bones, tissues, and organs experience no strain that could ever be noticed. The wave leaves no trace, no sensation, no memory in biological systems. And yet, for a brief moment, every object on Earth participates in a cosmic event, its geometry subtly altered by the motion of distant black holes. This universality is one of the most striking aspects of gravitational waves, and they do not discriminate between materials or scales. Everything responds in proportion to its size, but the relative change remains the same. This property allows detectors to operate by comparing lengths. It also means that gravitational waves provide a direct connection between distant events and local measurements, linking the largest structures in the universe to the smallest measurable changes on Earth. As waves propagate, they maintain a precise relationship between their amplitude and frequency. This relationship reflects the conservation of energy and momentum in space-time. During in-spiral, the frequency increases as the orbit tightens. During merger, it peaks sharply. During ring-down, it decays in a characteristic pattern. Each phase leaves a distinct imprint. By analyzing these imprints, many scientists can reconstruct the entire event, even though it occurred billions of light years away. The fidelity of this reconstruction depends on the wave's journey remaining largely unaltered. Gravitational waves fulfill this requirement better than any other known messenger. They do not scatter. They do not disperse in the way light does through plasma. Their form is preserved. This makes them reliable narrators of their own origins, carrying information with minimal distortion. On cosmological scales, gravitational waves also interact with the large-scale structure of the universe. The expansion of space stretches their wavelengths, reducing their frequency by the time they reach Earth. This effect is subtle but measurable. It provides insight into the rate at which the universe expands and how that expansion has changed over time. In this way, gravitational waves serve not only as probes of local events, but also as tools for studying cosmic evolution. The journey of a gravitational wave can span most of the age of the universe. A signal detected today may have been emitted when the universe was much younger, when galaxies were forming and stars were more abundant. During its transit, the wave passes through regions shaped by dark matter, through filaments connecting galaxy clusters, through voids of near emptiness. None of these environments significantly alter its structure. The wave carries its message intact across cosmic distances. This endurance contrasts sharply with light. Photons emitted at the same time as a gravitational wave may never reach Earth. They can be absorbed by gas, blocked by dust, or deflected by gravity into different paths. Entire epochs of cosmic history are hidden from electromagnetic observation because the universe was opaque to light during its early stages. Gravitational waves, by contrast, can pass through those early conditions, offering potential access to times otherwise inaccessible. The fact that gravitational waves pass through Earth continuously raises an intriguing realization. Even before detectors existed, Earth was being crossed by waves generated by distant events. Black hole mergers, neutron-star collisions, and other dynamic processes sent ripples outward that washed over the planet silently. Life evolved, civilizations rose and fell, unaware of these constant geometric vibrations. Detection did not create the phenomenon, it merely revealed it. This realization reframes the relationship between observer and universe. Our humans do not stand apart, watching events from a distance. They are embedded within a dynamic space-time, constantly influenced by distant motions. The effect is subtle, but the connection is real. Gravitational waves demonstrate that events occurring far beyond the reach of light can still influence local geometry, even if that influence is imperceptible. From a scientific perspective, this connection enables new tests of fundamental principles. The speed of gravitational waves, their polarization states, and their interaction with matter all reflect underlying laws. Measurements confirm that gravitational waves travel at the speed of light, consistent with current theories. Their polarization matches predictions for waves produced by space-time curvature. These confirmations strengthen confidence in existing models while narrowing the space for alternatives. At the same time, the precision required to detect gravitational waves pushes technology to its limits. Improvements in sensitivity require innovations in materials, optics, and control systems. Advances in these areas often find applications beyond astronomy, influencing fields such as precision measurement, data analysis, and engineering. The pursuit of gravitational waves thus drives progress across multiple disciplines. The quiet nature of gravitational waves also invites philosophical reflection. The most energetic events in the universe do not announce themselves with spectacle. They leave no bright scars on the sky. Instead, they reshape geometry in ways that require patience and subtlety to observe. This challenges assumptions about significance and visibility. It suggests that some of the universe's most important processes occur without display. As detection capabilities expand, the range of observable sources grows. Lower frequency detectors will capture waves from supermassive black hole mergers, events that unfold over years rather than seconds. These waves will reveal the growth of galaxies and the role of black holes in shaping large-scale structure. The gravitational spectrum will broaden, offering a more complete picture of cosmic dynamics. The study of gravitational waves thus bridges scales. It connects stellar remnants to galaxy formation, local measurements to cosmic expansion, transient events to persistent backgrounds. Each detection is both a specific observation and part of a larger pattern. Together, they form a coherent narrative of a universe defined by motion and change. Transforming gravitational waves into knowledge requires more than detection. It requires interpretation. The raw signal recorded by a detector is a time-dependent change in distance, a subtle oscillation buried within noise. On its own, this signal is not yet a story. It becomes meaningful only when it is compared to theoretical models that describe how space-time should behave under specific conditions. This comparison is the bridge between observation and understanding. Theoretical waveforms are generated using detailed calculations that combine analytical approximations with numerical simulations. These models predict how gravitational waves should look for black hole binaries of different masses, spins, and orientations. Each parameter leaves a distinct imprint on the waveform. Mass influences the overall scale and duration of the signal. Spin affects the phase and modulation. Orientation determines how strongly the wave interacts with the detector. By matching observed signals to these templates, scientists can infer the properties of the source. This process is inherently probabilistic. No measurement is perfect. Noise introduces uncertainty. Rather than producing a single answer, analysis yields ranges of possible values, each with associated confidence levels. These uncertainties are not weaknesses. They are integral to scientific rigor. They define what is known and what remains uncertain, guiding further observation and refinement. The analysis begins with data conditioning. Raw measurements contain a mixture of signals and noise. Environmental sensors record seismic activity, magnetic fields, and other disturbances that could affect the detector. These data are used to identify and remove spurious contributions. Calibration ensures that recorded changes correspond accurately to physical distances. Only after these steps is the data ready for waveform comparison. Pattern matching algorithms then search for correlations between the cleaned data and predicted waveforms. This search spans a vast parameter space, considering millions of possible combinations. High-performance computing is essential. Clusters of processors work in parallel, evaluating matches and estimating likelihoods. When a strong match emerges, it is examined closely, tested against alternative explanations, and compared across detectors. Once a signal is confirmed, further analysis extracts astrophysical meaning. The masses of the black holes are estimated, often with surprising precision. Their distance is inferred from the signal's amplitude. The energy radiated is calculated from the waveform's shape. In some cases, spin orientations can be constrained, offering insight into the system's formation history. Each parameter contributes to a more complete picture of the event. These reconstructions reveal that black hole mergers are not rare anomalies. They are common outcomes of stellar evolution. Massive stars live short lives. When they die, they often leave behind black holes. In regions where stars form in abundance, black holes form in abundance as well. Over time, some of these black holes pair up and merge, contributing continuously to the gravitational wave background. The population statistics derived from detections inform models of star formation and galactic evolution. They indicate how frequently massive stars form, how often they remain bound in binaries, and how environments influence their fate. Differences between predicted and observed populations prompt revisions to theory, improving understanding of stellar life cycles. Gravitational wave observations also constrain the physics of matter under extreme conditions. While black hole interiors remain inaccessible, the dynamics of mergers test gravity in its strongest regime. Deviations from predicted waveforms could signal new physics, such as additional dimensions or alternative theories of gravity. So far, observations align closely with established models, reinforcing their validity while narrowing the range of viable alternatives. Confidence in these conclusions arises from repetition. Each detection reinforces patterns seen before. Consistency across events builds trust. As the catalog grows, outliers become apparent, inviting closer scrutiny. Rare events can be identified and studied in depth, revealing new aspects of cosmic behavior. The translation of gravitational waves into sound, often used for public communication, is a metaphor rather than a literal representation. Frequencies are shifted into the audible range to illustrate patterns. This translation helps convey the structure of signals, but the true phenomenon remains geometric. The waves do not vibrate air. They vibrate space itself. Sound is an analogy, a bridge between abstract measurement and human perception. Despite this abstraction, the information carried by gravitational waves is concrete, and it reveals motions that cannot be seen. It confirms predictions made decades earlier. It demonstrates that space-time is dynamic, responsive, and measurable. These insights reshape the conceptual foundation of astronomy. The act of listening, in this context, is not passive. It requires active interpretation, careful validation, and continual refinement. Listening means extracting meaning from subtle signals, acknowledging uncertainty, and remaining open to revision. It is a discipline that values patience and precision over spectacle. As detection techniques improve, analysis methods evolve. Machine learning algorithms assist in identifying patterns and classifying signals. Advanced simulations capture more complex dynamics. The interplay between observation and theory becomes tighter, each informing the other. This synergy accelerates discovery. Beyond individual events, gravitational wave data contribute to a cumulative understanding of the universe. They provide independent measurements of cosmic expansion. They trace the distribution of mass across time. They offer glimpses into epochs otherwise hidden from view. Each wave adds a thread to a larger tapestry. The universe, viewed through gravitational waves, is not static or silent. It is restless, constantly adjusting its geometry in response to motion. This restlessness is not chaotic. It follows precise laws. Understanding those laws requires careful listening, attentive analysis, and respect for subtlety. Gravitational waves change more than observational technique. They change perspective. Before their detection, the universe was understood primarily through light, a medium that favors objects that shine, reflect, or heat their surroundings. This emphasis shaped intuition. Bright galaxies appeared important. Violent explosions drew attention. Darkness suggested absence. Gravitational waves overturn that bias. They reveal a universe where significance is not tied to visibility, where the most massive and influential events may occur without producing light at all. Black holes exemplify this shift. For decades, Their existence was inferred indirectly through the behavior of nearby matter. Stars orbited unseen companions. Gas disks heated and emitted radiation before disappearing across invisible boundaries. These observations suggested black holes, but they did not capture the objects themselves in motion. Gravitational waves changed that. They allowed direct observation of black holes interacting, merging, and reshaping space-time. The universe's darkest objects became among its most informative. This shift also alters the concept of distance. In traditional astronomy, distance often correlates with dimness. Objects farther away appear fainter, harder to study. Gravitational waves weaken with distance as well, but their interpretation differs. The waveform itself encodes absolute scale. Distance becomes a geometric property extracted from space-time's response, not an estimate inferred from brightness. This reframing strengthens confidence in measurements and reduces dependence on assumptions. Listening to gravitational waves also emphasizes time in a new way. Light offers snapshots. A photon arrives carrying information from a specific moment. Gravitational waves, by contrast, often carry extended histories. The in-spiral phase of a merger records a long sequence of orbits, compressed into seconds of signal. This compression allows observers to witness millions of years of evolution in moments. Time becomes layered, revealing processes that unfold slowly yet culminate rapidly. The concept of silence takes on new meaning. Silence does not indicate inactivity. It indicates a mode of communication beyond ordinary senses. The universe is not quiet because nothing happens. It is quiet because its most fundamental motions do not disturb air or produce light. Gravitational waves demonstrate that absence of sound does not imply absence of signal. Instead, it invites different forms of attention. This realization influences how science approaches the unknown. Instead of asking only what can be seen, researchers ask what can be inferred from subtle effects. They search for consequences rather than direct manifestations. This approach expands the scope of inquiry, opening avenues previously considered inaccessible. Gravitational waves also encourage humility. The signals detected are extraordinarily faint. Their measurement requires acknowledging limitations, embracing uncertainty, and refining methods continually. Each detection is provisional, subject to revision as understanding improves. This humility contrasts with narratives of conquest or dominance. Listening replaces capture. Interpretation replaces control. From a broader perspective, gravitational waves underscore the interconnectedness of the cosmos. Events occurring in distant galaxies influence measurements on Earth. The geometry of space-time links regions separated by billions of light years. This linkage is not metaphorical. It is encoded in measurable distortions that pass through all matter. The universe is unified not only by physical laws, but by shared geometry. This unity extends across scales. Stellar remnants influence galactic evolution. Galactic mergers shape large-scale structure. All these processes generate gravitational waves that propagate outward, contributing to a collective background. The universe is filled with overlapping signals, a constant geometric activity that reflects its history and structure. As more detections accumulate, patterns emerge that challenge assumptions. Black hole masses span wider ranges than expected. Merger rates vary with cosmic time. Environments influence outcomes in subtle ways. And these observations prompt revisions to models of star formation, binary evolution, and galactic dynamics. Gravitational waves thus drive progress not only in gravitational physics, but across astrophysics. The expansion of gravitational wave astronomy also raises questions about what remains undetected. Sensitivity limits define current horizons. Beyond them lie events too distant, too weak, or too slow to observe. These unseen processes still shape the universe. Acknowledging their existence reminds observers that knowledge is partial, bounded by technology and perspective. Future detectors promise to extend reach. Space-based observatories will detect lower-frequency waves, revealing mergers of supermassive black holes and the slow dance of compact objects orbiting massive centers. These observations will illuminate the growth of galaxies and the role of gravity in shaping cosmic architecture. As detection spans more frequencies, the gravitational wave spectrum will resemble an orchestra with many sections. High-frequency chirps from stellar mass mergers, low-frequency hums from massive systems, persistent backgrounds from countless unresolved sources. Each contributes to a richer understanding of cosmic dynamics. Listening to this spectrum requires patience and adaptation. Different frequencies demand different instruments. Analysis techniques must evolve. Collaboration becomes increasingly important. No single observatory can capture the full range. A network of detectors operating across scales becomes essential. This collaborative approach reflects the nature of the phenomenon itself. The gravitational waves are global. They do not belong to one region or observer. Their detection requires collective effort. Data is shared. Methods are refined together. Discoveries are confirmed through consensus. This communal process mirrors the interconnected universe being studied. Beyond science, gravitational waves influence how humanity conceives its place in the cosmos. They emphasize participation over observation. Earth is not merely a platform for viewing distant events. It is part of the medium through which those events propagate. The planet's geometry responds, however subtly, to distant motions. This participation blurs the boundary between observer and observed. In recognizing this, gravitational wave astronomy invites a quieter form of engagement with the universe. It values listening over looking, patience over immediacy. It acknowledges that some truths reveal themselves only through sustained attention to subtle change. Gravitational waves rarely exist in isolation from other cosmic signals, even when they themselves are silent. In some cases, the events that generate them also produce light, particles, or other forms of radiation. When these multiple messengers are observed together, they offer a more complete picture of what occurred. This approach, known as multi-messenger astronomy, combines different kinds of information to deepen understanding of complex phenomena. Neutron star mergers provide the clearest example. When two neutron stars spiral together and collide, they emit gravitational waves as well as intense bursts of electromagnetic radiation. These bursts can appear as short gamma-ray flashes, followed by afterglows across the spectrum, from X-rays to radio waves. The gravitational waves reveal the motion and masses of the stars. The light reveals the behavior of matter under extreme pressure and temperature. Together, they tell a story that neither could tell alone. In these events, gravitational waves arrive first, traveling directly through space-time. Light follows, often delayed by interactions with surrounding matter. This sequence allows precise timing comparisons. By measuring how quickly each signal arrives, scientists can test whether different messengers travel at the same fundamental speed. Observations so far confirm that gravitational waves and light propagate at essentially the same speed, reinforcing key assumptions about space-time and causality. Multi-messenger observations also shed light on the origins of heavy elements. When neutron stars merge, they eject matter rich in neutrons. This matter undergoes rapid nuclear reactions, forming elements heavier than iron, such as gold and platinum. Gravitational waves identify the merger. Optical and infrared observations track the radioactive glow of newly formed elements. This connection links cosmic motion to the material composition of planets and life. Black hole mergers, by contrast, often occur without accompanying light. This absence is itself informative. It indicates environments devoid of significant matter. The silence in electromagnetic channels confirms theoretical expectations. Gravitational waves thus provide confirmation not only through presence, but through absence, ever reinforcing understanding of different cosmic contexts. The integration of multiple messengers requires coordination. Gravitational wave detectors alert observatories worldwide when a potential event occurs. Telescopes then search the sky for transient signals. This rapid response transforms fleeting distortions into opportunities for comprehensive study. The success of such coordination depends on global collaboration and shared infrastructure. As detection networks expand, the likelihood of multi-messenger observations increases. Improved localization narrows search areas. Faster analysis accelerates alerts. Broader coverage increases chances of capturing transient light. Each improvement enhances the scientific return of individual detections. Beyond individual events, multi-messenger data refine models of astrophysical processes. Comparing gravitational wave signals with electromagnetic counterparts constrains theories of matter behavior, radiation mechanisms, and energy release. Discrepancies prompt revision. Agreement strengthens confidence. This iterative process drives progress. Gravitational waves also complement other non-electromagnetic messengers, such as neutrinos. These nearly massless particles travel vast distances with little interaction. Joint detections of neutrinos and gravitational waves could reveal processes involving dense matter and extreme acceleration. While such coincidences remain rare, they represent a frontier of observational capability. The synthesis of messengers underscores the complexity of cosmic events. No single channel captures all aspects. Motion, matter, and radiation each reveal different facets. Gravitational waves emphasize dynamics. Light reveals composition and temperature. Particles trace energetic interactions. Together, they provide a multi-dimensional view. This multi-dimensional approach influences future observatory design. Instruments are planned with coordination in mind. Sensitivity, coverage, and timing are optimized to enable joint observations. Data sharing becomes integral. The boundaries between disciplines blur as astronomers, physicists, and engineers collaborate. Multi-messenger astronomy also deepens the philosophical implications of gravitational waves. It illustrates that silence and sound, darkness and light are not opposites, but complements. Each conveys different information. Listening to space-time does not replace seeing the universe. It enriches it. As gravitational wave catalogs grow, statistical combinations with electromagnetic surveys become possible. Patterns across populations emerge. Correlations between merger rates and galactic environments can be explored. Connections between star formation history and compact object mergers become clearer. These insights refine models of cosmic evolution. The integration of messengers also aids in addressing open questions about gravity itself. Comparing how different signals propagate tests fundamental principles. Any discrepancy would signal new physics, The consistency observed so far reinforces existing frameworks, while continued vigilance keeps the door open to discovery. Listening to the universe through multiple channels requires adaptability. Instruments must be sensitive, responsive, and cooperative. Analysis must be flexible, incorporating diverse data types. This adaptability mirrors the dynamic universe being studied. The future of gravitational wave astronomy extends far beyond current capabilities. Existing detectors are sensitive to a specific range of frequencies, primarily those produced by mergers of stellar mass black holes and neutron stars. Yet the universe generates gravitational waves across a vast spectrum. Lower frequency waves arise from far more massive systems, while higher frequency waves emerge from smaller, faster processes. Expanding sensitivity across this spectrum promises to reveal an even richer portrait of cosmic motion. Space-based observatories represent one of the most significant steps forward. Freed from terrestrial noise, these detectors will measure gravitational waves at frequencies inaccessible from Earth. They will consist of spacecraft separated by millions of kilometers, linked by laser beams that monitor changes in distance caused by passing waves. This scale allows detection of signals produced by supermassive black hole mergers, events that unfold slowly over months or years rather than seconds. Supermassive black holes reside at the centers of most galaxies. When galaxies merge, their central black holes are drawn together, eventually forming binaries. These binaries emit low-frequency gravitational waves as they orbit and spiral inward. Detecting these signals will reveal how galaxies grow and evolve over cosmic time. It will illuminate the role of gravity in shaping large-scale structure and provide direct measurements of black hole growth. In addition to discrete mergers, your space-based detectors will observe continuous signals from compact objects orbiting massive black holes. These systems, known as extreme mass ratio in spirals, involve a small object slowly circling a much larger one. The gravitational waves emitted trace the space-time geometry around the massive black hole in exquisite detail. By analyzing these waves, scientists can test gravity in regimes of extreme curvature, probing aspects of space-time otherwise inaccessible. Ground-based detectors will continue to improve as well. Enhancements in laser power, mirror quality, and noise suppression will extend sensitivity. These improvements will increase detection rates, capturing more events and enabling finer statistical studies. As catalogs grow, subtle trends will emerge, revealing how black hole properties depend on environment and cosmic epoch. The expansion of detection networks also improves localization. With more detectors distributed globally, signals can be pinpointed more precisely. This precision enhances coordination with other observatories, facilitating multi-messenger observations. Rapid localization allows telescopes to search for counterparts promptly, maximizing scientific return. Beyond planned observatories, conceptual designs explore even more ambitious ideas. Lunar-based detectors could take advantage of the moon's seismic quiet. Atom interferometers may offer new ways to measure space-time distortions. Each concept reflects the same underlying goal: listening more carefully to the universe's geometry. As sensitivity increases, previously hidden sources may emerge. Continuous backgrounds generated by countless distant mergers may be resolved into individual events. Rare phenomena, such as mergers involving intermediate mass black holes, may be detected. These discoveries would fill gaps in understanding of black hole populations and formation pathways. The growing reach of gravitational wave astronomy also intersects with cosmology. Precise distance measurements from waveforms can refine estimates of the universe's expansion rate. Comparing these measurements with other methods may help resolve existing tensions in cosmological parameters. Gravitational waves thus contribute not only to astrophysics, but to understanding the universe's overall behavior. Future observations may also probe physics beyond current models. These subtle deviations in wave propagation or waveform structure could hint at new forces or dimensions. Detecting such deviations requires both sensitivity and confidence, built through repeated observation and rigorous analysis. The possibility of discovery motivates continual refinement. The expanding symphony of gravitational waves invites a shift in how cosmic history is reconstructed. Instead of relying solely on light, history is inferred from motion. The merging of black holes becomes a record of stellar evolution, galactic interaction, and cosmic structure formation. Each wave carries traces of its origin, connecting present measurements to distant past events. This approach also changes how silence is perceived. Silence is no longer absence, but a different mode of information. The universe speaks in geometry as well as radiation. Learning to listen requires patience, precision, and openness to subtlety. As humanity's listening abilities grow, so does its awareness of connection. Events occurring far beyond the reach of light influence local measurements. The universe is not a collection of isolated regions, but a continuous fabric responsive to motion everywhere. Gravitational waves reveal this continuity, making it measurable. The human effort behind gravitational wave discovery is as quiet and patient as the signals themselves. Unlike dramatic moments often associated with scientific breakthroughs, progress in this field unfolded gradually, shaped by decades of incremental advances, careful planning, and long periods without confirmation. Researchers worked with the understanding that success was uncertain, that years of effort might yield only upper limits or null results. This acceptance of uncertainty became a defining characteristic of the field. Building instruments capable of detecting gravitational waves required collaboration across disciplines. Physicists, engineers, material scientists, computer scientists, and statisticians contributed expertise. Each challenge revealed another layer of complexity. Reducing seismic noise required understanding Earth's motion. Stabilizing lasers required advances in optics. Interpreting data demanded sophisticated algorithms. No single insight solved the problem. Progress emerged from accumulation. Many early experiments failed to reach the sensitivity required for detection. These failures were not setbacks, but learning experiences. Each iteration revealed new sources of noise, new limitations, and new opportunities for refinement. The field advanced through persistence rather than sudden revelation. This slow progress mirrored the phenomena being studied. Gravitational waves themselves are subtle, requiring patience to observe. The first confirmed detections were the culmination of this collective effort. They validated not only theoretical predictions, but also decades of experimental dedication. For many involved, the moment was quiet rather than celebratory. Confirmation came through careful checks, cross-validation, and repeated analysis. Confidence emerged gradually, reinforced by consistency across detectors and alignment with theory. This culture of caution remains central. Every detection undergoes scrutiny. Claims are conservative. Uncertainty is acknowledged openly. This discipline ensures that conclusions are robust and that the field advances on firm foundations. Listening to space-time requires restraint as much as curiosity. The collaborative nature of gravitational wave astronomy extends globally. Observatories operate on different continents. Data is shared across borders. Analysis teams span time zones and cultures. This global cooperation reflects the universal nature of the phenomena being studied. Gravitational waves belong to no single nation. They pass through Earth indiscriminately, inviting shared exploration. Training the next generation of researchers is an integral part of this effort. Students learn not only technical skills, but also the values of patience, collaboration, and rigor. They inherit a field shaped by long-term thinking, where success may come years after initial work begins. This perspective influences how problems are approached, emphasizing sustainability over immediacy. The human dimension also includes adaptability. As detectors improve and data volumes increase, methods evolve. Researchers must continually update tools, learn new techniques, and integrate advances from other fields. This adaptability keeps the field responsive and innovative, capable of extracting meaning from increasingly complex datasets. Public engagement plays a role as well. Communicating discoveries requires translating abstract concepts into accessible narratives without sacrificing accuracy. Metaphors help bridge understanding, but care is taken to avoid oversimplification. The challenge is to convey significance while respecting nuance, inviting curiosity without distorting meaning. Gravitational wave discoveries have influenced public perception of science. They demonstrate that profound insights can emerge from quiet persistence rather than spectacle. They highlight the value of basic research, pursued without immediate application in mind. This example reinforces the importance of investing in long-term inquiry. The field also illustrates how theoretical predictions can precede observation by decades. Gravitational waves were predicted long before technology existed to detect them. This gap underscores the interplay between theory and experiment. Theory guides exploration. Experiment tests and refines theory. Together, they advance understanding. As listening continues, the relationship between humanity and the cosmos evolves. Detection does not diminish mystery. It deepens it. Each answer raises new questions. What remains undetected? What lies beyond current sensitivity? What surprises await in unexplored frequency ranges? These questions sustain curiosity. The patience required to pursue such questions shapes scientific culture. It fosters respect for uncertainty and appreciation for incremental progress. It encourages collaboration over competition. These values extend beyond gravitational wave astronomy, influencing broader approaches to knowledge. Silence, when viewed through the lens of gravitational waves, becomes a concept that requires revision. In everyday experience, silence implies stillness, inactivity, or absence. It suggests that nothing is happening, that motion has ceased, that information is unavailable. Gravitational waves reveal a different reality. A silence does not indicate a lack of events. It indicates a lack of sensory translation. The universe can be active, dynamic, and profoundly energetic without producing anything that ears or eyes can detect. This distinction reshapes how cosmic events are understood. Black holes collide without sound, not because the event lacks intensity, but because sound requires a medium. In the vacuum of space, there is no air to carry pressure waves. Gravitational waves bypass this requirement entirely. They do not rely on matter to transmit motion. They are motion, expressed directly through geometry. Their silence is not emptiness, but purity. Distance also acquires a new meaning. Traditionally, distance separates observers from events. The farther something is, the less influence it seems to have. Gravitational waves undermine this intuition. A merger occurring billions of light years away still alters the geometry of space at Earth, however faintly. Distance attenuates amplitude, but it does not sever connection. Space-time itself maintains continuity across vast scales. This continuity implies that the universe is less fragmented than it appears. Regions separated by immense distances are linked by shared geometry. Motion in one place subtly influences geometry everywhere. Gravitational waves make this linkage measurable. They reveal that separation is not isolation. It is a gradient of influence. Presence, too, is reframed. Presence is often associated with proximity or visibility. Something is present if it can be seen, touched, or heard. Gravitational waves introduce a different form of presence. An event can be present through its effect on space-time, even if no other signal accompanies it. Presence becomes geometric rather than sensory. This geometric presence challenges human-centered definitions of observation. It suggests that reality extends beyond what is directly perceptible. Instruments become extensions of perception, translating subtle effects into forms that can be analyzed. Observation becomes an act of interpretation rather than direct encounter. Gravitational waves also highlight the layered nature of reality. Multiple processes occur simultaneously, each operating on different scales and through different channels. Light, particles, and space-time geometry coexist, each carrying information. No single channel is complete. Understanding emerges from synthesis. This layered view encourages openness to complexity. It resists reduction to simple narratives. It acknowledges that some aspects of the universe require indirect approaches. Listening to space-time exemplifies this approach, demanding patience and precision. The concept of connection extends beyond physical influence. Gravitational waves connect present observers to ancient events. Signals detected today originated long before Earth formed. This temporal connection collapses epochs into moments of measurement. Time becomes a dimension through which information travels, linking disparate eras. This linkage invites reflection on humanity's place in cosmic history. Observers are not merely passive recipients of information. They participate in a continuum, measuring effects that originated under entirely different conditions. Detection becomes an act of historical reconstruction, piecing together stories written into space-time. Because the persistence of gravitational waves also suggests durability of information. While matter changes and radiation scatters, geometric distortions endure across cosmic distances. They preserve aspects of events that might otherwise be lost. This durability offers a form of cosmic memory, encoded in the structure of space-time. As listening capabilities improve, this memory becomes clearer. Patterns emerge. Histories can be traced. The universe reveals itself not as static scenery, but as an evolving narrative recorded in motion. Gravitational waves are chapters in that narrative, each describing a transformation. This perspective influences not only science, but philosophy. It challenges assumptions about causality, presence, and significance. It suggests that influence does not require immediacy, that meaning can be carried silently, that connection persists despite separation. The quiet nature of gravitational waves aligns with these themes. They do not demand attention. They require it. They reward careful listening rather than passive reception. In this way, they exemplify a mode of engagement that values attentiveness over intensity. As the field advances, these conceptual shifts may deepen. New detections may reveal phenomena that further challenge intuition. Each discovery expands the framework through which the universe is understood. Silence becomes richer. Distance becomes nuanced. Presence becomes layered. Gravitational waves offer a rare opportunity to study the universe at times far earlier than any direct observation with light allows. In the earliest moments after the universe began expanding, conditions were radically different from those seen today. Temperatures were extreme. Matter existed in unfamiliar forms. The universe was opaque to light, filled with charged particles that scattered photons before they could travel freely. For hundreds of thousands of years, light could not move unimpeded. Information carried by radiation was trapped. Gravitational waves, however, were not. Because gravitational waves interact so weakly with matter, they could propagate through the early universe almost immediately. If violent processes occurred during those early moments, they would have generated ripples in space-time that continued outward, carrying information from epochs otherwise hidden. Detecting such primordial gravitational waves would provide direct evidence of physical processes that shaped the universe at its birth. Yes, several mechanisms could have produced gravitational waves in the early universe. Rapid expansion, phase transitions, and the formation of fundamental structures all involve large-scale motion of energy and space-time. If the universe underwent periods of accelerated expansion, known as inflation, quantum fluctuations could have been amplified into macroscopic distortions of space-time. These distortions would leave a faint but persistent gravitational wave background, permeating the universe today. Unlike gravitational waves from black hole mergers, primordial waves would not arrive as isolated events. They would form a continuous background, a subtle geometric texture underlying space-time. Detecting this background is extraordinarily challenging, and its signal is expected to be much weaker than astrophysical sources and spread across a broad range of frequencies. Distinguishing it from other backgrounds requires long-term observation and careful separation of contributions. Despite these challenges, efforts continue. Measurements of cosmic microwave background polarization provide indirect constraints on primordial gravitational waves. Certain patterns in the polarization of light may reflect the influence of early space-time distortions. While definitive detection remains elusive, these observations narrow the range of possible models, refining understanding of the universe's earliest behavior. Gravitational waves from later cosmic epochs also carry information about structure formation. As the universe evolved, matter clumped under gravity, forming stars, galaxies, and clusters. The motion of these structures generated gravitational waves, contributing to the background. By analyzing this background, scientists can infer how structure formation progressed and how matter was distributed over time. The study of early universe gravitational waves intersects with fundamental physics. Conditions shortly after expansion began involve energies far beyond those accessible in laboratories. Gravitational waves may offer clues about particle physics at these scales, potentially revealing new fields, symmetries, or interactions. This makes gravitational wave astronomy a bridge between cosmology and high-energy physics. Understanding these early signals requires disentangling multiple contributions. Astrophysical sources produce a background that may obscure primordial signals. Careful modeling and cross-correlation with other observations help separate these components. This work is ongoing, requiring patience and refinement. The potential rewards are significant. Detecting primordial gravitational waves would provide direct evidence of processes that shaped the universe's initial conditions. It would inform models of inflation, constrain theories of fundamental forces, and deepen understanding of how space-time itself emerged. Even without direct detection, gravitational wave astronomy contributes to early universe studies through exclusion. By setting upper limits on background strength, observations rule out certain models. This narrowing guides theoretical development, focusing attention on viable scenarios. As listening extends across frequencies and sensitivities improve, the window into cosmic origins widens. Gravitational waves promise access to epochs otherwise unreachable. They offer a way to study beginnings without relying on light, using geometry as a record. This geometric record emphasizes continuity. The same space-time that vibrates today vibrated in the past. The universe's earliest motions left imprints that persist, linking present measurements to ancient events. This continuity reinforces the idea that cosmic history is not lost, but encoded. The challenge lies in learning how to read this encoding. Signals are faint. Backgrounds overlap. Interpretation demands rigor. Yet progress continues, driven by curiosity and persistence. The universe does not produce gravitational waves only in rare, dramatic moments. It produces them continuously. At any given time, countless systems across cosmic distances are in motion, generating ripples that spread outward and overlap. Individually, most of these waves are too faint or too distant to be resolved. Together, they form a persistent gravitational wave background, a steady geometric hum that fills space-time. This background is not uniform noise. It is structured, shaped by the population of sources that contribute to it. Black hole mergers, neutron star binaries, and other compact systems all add their signatures. The cumulative effect reflects the history of star formation, the distribution of mass, and the rate at which compact objects form and merge throughout the universe. Listening to this background is like listening to an orchestra from afar, where individual instruments blur into a collective sound. Detecting the gravitational wave background requires different techniques than detecting individual events. Instead of searching for transient signals, scientists analyze long stretches of data, looking for correlated patterns that persist over time. This analysis demands exceptional stability and sensitivity. Small systematic errors can mimic background signals. Careful statistical methods are essential to distinguish genuine cosmic contributions from instrumental artifacts. The background's properties vary with frequency. At higher frequencies, the background is dominated by stellar mass binaries. At lower frequencies, contributions from supermassive black hole binaries become significant. Each frequency band reveals different aspects of cosmic evolution. Together, they form a layered portrait of the universe's dynamic history. The gravitational wave background also encodes anisotropy. It is not perfectly uniform across the sky. Regions with higher concentrations of galaxies contribute more strongly. Large-scale structures leave subtle imprints. Mapping these variations can reveal how matter is distributed on cosmic scales, complementing observations made with light. As sensitivity improves, portions of the background may be resolved into individual sources. This transition blurs the line between background and discrete events. What once appeared as noise becomes signal. This progression mirrors the history of astronomy, where unresolved light gradually yielded to detailed observation as instruments improved. Understanding the background requires integrating astrophysics, cosmology, and data science. Models predict contributions based on population synthesis. Observations constrain these models. Discrepancies prompt revision. This iterative process refines understanding of how cosmic populations evolve. The background also offers a way to probe events beyond detection thresholds. Even if individual mergers are too distant to observe directly, their combined effect can be measured. This expands observational reach, allowing inference about populations otherwise inaccessible. The persistent nature of the background emphasizes continuity. The universe's motion does not pause between events. It is ongoing. Gravitational waves accumulate, overlap, and propagate, reflecting a universe in constant adjustment. Silence, once again, reveals itself as activity beyond perception. Listening to this background requires long-term commitment. Signals accumulate slowly. Statistical confidence builds over time. Patience is rewarded with insight. This approach aligns with the broader ethos of gravitational wave astronomy, where progress is measured in years rather than moments. The gravitational wave background also intersects with fundamental physics. Its spectrum may contain signatures of early universe processes, phase transitions, or exotic phenomena. Distinguishing these contributions from astrophysical backgrounds is challenging, but potentially transformative. As techniques mature, the background becomes a tool for exploration rather than an obstacle. What once obscured signals becomes a subject of study. The hum of space-time turns into a record of collective motion, preserving information across epochs. This collective motion reinforces the idea that the universe is not a collection of isolated events. It is a continuous process. Individual mergers are moments within a larger flow. Gravitational waves capture this flow, encoding it in geometry. The continuous gravitational wave background reshapes how cosmic time is perceived. In traditional observation, events are separated by clear boundaries. A supernova explodes. A galaxy shines. A signal arrives, is recorded, and then passes into history. Gravitational waves blur these boundaries. Signals overlap. Waves from different eras coexist, arriving together at Earth despite originating millions or billions of years apart. Time, as experienced through space-time vibrations, becomes layered rather than sequential. This layering challenges linear narratives of cosmic history. The present moment contains echoes of countless past events. A detector listening now is, in effect, listening to a superposition of times. Each wave carries its own origin, but they arrive intertwined, indistinguishable without careful analysis. This convergence collapses temporal distance, allowing the past to influence present measurements directly. Gravitational waves thus redefine what it means for an event to be over. A black hole merger may conclude in seconds at its source, but its influence persists as waves continue to travel outward. Those waves cross interstellar space, pass between galaxies, and eventually reach observers long after the original system has settled into quiet stability. The event remains active in the universe's geometry long after its local conclusion. This persistence emphasizes that cosmic processes are not confined to their immediate vicinity. They extend outward, influencing space-time across vast regions. The universe records these processes not in archives, but in its structure. Gravitational waves are inscriptions written into geometry, legible wherever they pass. Listening to space-time reveals that the universe is filled with memory. This memory is not stored in matter, but in motion. It is preserved through propagation rather than accumulation. Each wave is a message that does not fade easily, carrying information across cosmic distances with remarkable fidelity. This perspective alters the distinction between observer and event. Observers do not merely detect remnants. They encounter ongoing effects. A detection is not a glimpse into the past. but an interaction with a wave that is still propagating. The observer becomes part of the wave's journey, measuring its influence at a particular location in space-time. The notion of simultaneity also becomes nuanced. Waves generated at different times arrive together, creating a present composed of multiple pasts. Analysis disentangles these contributions, reconstructing histories from overlapping signals. This process requires careful separation, distinguishing individual patterns within the collective hum. Gravitational wave astronomy thus operates at the intersection of timescales. It compresses long evolutionary processes into brief measurements. It stretches brief events into long-lasting influences. This flexibility challenges intuition, but offers deeper insight into cosmic dynamics. The interplay between background and discrete events exemplifies this complexity. Individual mergers stand out against the background, but they also contribute to it. Over time, the accumulation of events shapes the background, while the background informs interpretation of individual signals. This feedback loop reflects the interconnected nature of cosmic processes. Understanding this interplay demands statistical thinking. Individual detections provide detailed information about specific systems. The background reveals aggregate properties. Together, they offer a comprehensive view of cosmic motion, from singular events to collective trends. This comprehensive view influences models of cosmic evolution. It informs estimates of how often black holes merge, how these rates change over time, and how they correlate with star formation history. Gravitational waves thus contribute to understanding not only dramatic events, but long-term patterns. The layered time perspective also invites reflection beyond science. It suggests that the present is not isolated. It is shaped by influences that began long ago. Connection across time becomes tangible, encoded in measurable geometry. As listening continues, sensitivity increases, and temporal layering becomes more pronounced. More distant events contribute. Backgrounds grow richer. Analysis becomes more complex. Each improvement deepens understanding. Gravitational waves reveal a universe in which vastly different scales coexist within a single physical framework. At one extreme, detectors measure changes in distance smaller than an atomic nucleus. At the other, these changes originate from events involving masses many times greater than stars and regions of space larger than solar systems. This connection between the infinitesimal and the immense is not incidental. It reflects the nature of space-time itself, where scale does not isolate phenomena, but links them through geometry. The stretching and compression caused by a gravitational wave is fractional. It scales with the size of the system experiencing it. A detector arm kilometers long changes by a tiny amount. A mountain range changes by more. A galaxy changes by vastly more. Yet the relative change remains consistent. This proportionality allows a single wave to influence structures across orders of magnitude in size simultaneously, unifying scale through motion. This property challenges intuition shaped by everyday experience. In familiar contexts, small causes produce small effects, and large causes produce large effects. Gravitational waves defy this simplicity. An event occurring far away produces a minute effect locally, yet that effect is a direct consequence of extreme cosmic motion. The connection is precise, mathematical, and indifferent to scale. The same framework governs planetary orbits, stellar evolution, and galactic dynamics. Gravity shapes motion across all these scales, curving space-time in response to mass and energy. Gravitational waves represent time-dependent changes in this curvature. They are the dynamic counterpart to static gravitational fields, revealing how geometry responds to motion. This unification extends to measurement itself. Instruments designed to detect gravitational waves rely on quantum properties of light, on classical mechanics of suspension systems, and relativistic descriptions of space-time. The detection process integrates physics across domains, demonstrating that understanding emerges from synthesis rather than isolation. The coexistence of scales also influences interpretation. Small uncertainties in measurement can correspond to large uncertainties in inferred properties of distant systems. Careful calibration and modeling are essential to ensure accuracy. This sensitivity reinforces the importance of rigor in analysis. Gravitational wave astronomy thus becomes an exercise in balance. It balances sensitivity and stability, resolution and noise suppression, theory and observation. Each aspect must be tuned carefully. Excessive sensitivity amplifies noise. Insufficient sensitivity misses signals. Achieving equilibrium mirrors the equilibrium sought in understanding. The influence of scale also affects future exploration. Detecting lower frequency waves requires instruments of immense size. Detecting higher frequency waves demands extreme precision. Each region of the spectrum poses distinct challenges, shaped by the scale of the sources and the effects to be measured. The ability to link scales transforms how cosmic structures are studied. Black hole mergers inform models of galaxy formation. Stellar evolution influences gravitational wave backgrounds. Large-scale structure leaves imprints on wave propagation. These connections encourage holistic approaches to astrophysics. Scale also intersects with time. Small-scale measurements capture brief events. Large-scale phenomena unfold over long durations. As gravitational waves compress these durations into accessible signals, allowing observation of slow processes through rapid measurement. This compression highlights the efficiency of geometric communication. Space-time carries information about motion efficiently across scales and times. Gravitational waves are the carriers of this information, bridging gaps that would otherwise remain unconnected. Understanding this bridging role requires conceptual flexibility. It requires accepting that measurement does not correspond directly to experience, that imperceptible changes can encode profound events. This acceptance expands the scope of inquiry. As listening continues, new scales may become accessible. Advances in technology may allow detection of waves from sources currently beyond reach. Each expansion of scale enriches understanding, revealing new connections. In the next section, we will explore how these insights influence interpretations of cosmic order and randomness, how gravitational waves reflect both predictability and unpredictability, and how listening to space-time reveals patterns emerging from apparent chaos.